Right, so thanks for coming to this session, Computer Vision and Machine Learning for XR1. So we have 4 great papers to present. The first paper is Gesture-to-Text, a generalizable decoder for word gesture keyboards in XR through trajectory coarse discretization and pre-training. The authors are Junxiao Shen, Khadija Khaldi, Enmin Zhou, Hemant Bhaskar Surale, and Amy Karlson. The presenter is Junxiao Shen. Junxiao?
Hi everyone, my name is Junxiao Shen. You can call me Sean, and today I'm excited to present our work titled Gesture-to-Text. So this work is in collaboration with my coworkers at Meta, and today I'll be mainly discussing how our proposed gesture-to-text system really enhances text input for XR environments, especially for AR and VR. Word gesture keyboards are really widely used in various XR environments, such as augmented, such as AR and VR. As you can see, in Oculus and HoloLens, they all have the word gesture keyboards implemented in their inbuilt system already. And these systems really offer natural and intuitive methods for text input, but they come with pretty significant challenges. Because different interaction methods, whether it's mid-air interaction or on surface-based interaction, they really introduce quite noisy inputs and very diverse patterns. As you can see over there, we studied 5 different interaction modes, and we've discovered that all the five different interaction modes, together with different layouts, the data patterns really varies for different interaction modes, for different behavior modes, and for different layout modes as well. So this leads to our key research question: how can we design a decoding method that is both generalizable across different interaction systems, different word gesture keyboard systems, and also robust enough to maintain high accuracy in very noisy environments? So previous approach for decoding word gesture typically fall into 2 categories. One is template matching, and the other one is neural decoder. So the most notable template matching system is called SHARK2, which is developed by my supervisor, Kristensson. And this is really widely used and is very simple to implement and very explainable. But it is quite sensitive to noise and struggles with out-of-vocabulary words. And on the other hand, neural decoders, like those proposed by Ashraf and also more recently by our own team, we offer improved accuracy by training deep neural networks on a large data set that we collect ourselves. But they really require large data sets and are often more complex to implement because you sort of need to collect the data yourself and train the model yourself, implement model yourself. So our work here aims to bridge this gap by creating a system that is both accurate and easy to implement, overcoming the limitation of these traditional approaches. The goal of our research is to create a decoder that combines high accuracy with ease of implementation across various word gesture systems. However, there are several challenges. XR environments vary significantly in terms of interaction modes, keyboard sizes, and user behaviors, which results in very different trajectory data patterns. And our goal is to design a generalizable method that can adapt to these diverse environments while maintaining accuracy and efficiency. So our solution is the gesture-to-text decoder. So it introduces a novel method called Coarse Discretization to simplify the complexity of gesture inputs. So the traditional gesture inputs are in this kind of 2D Cartesian coordinates, and so this techniques converts the continuous gesture trajectory into discrete pixels on the keyboard. And we also use one-hot encoding to further reduce sensitivity to input noise and improve the decoder's performance. And this approach really allows us to pre-train the decoder on the super large data set, similar to how large language models are pre-trained. As a result, the system becomes more robust and very generalizable across different word gesture keyboard systems. So for our experimental setup, we trained the gesture-to-text decoder using both synthetic and real-world data called how we swipe, and also synthetic data set that we That's from one of my previous paper that we were using GAN to synthesize the gesture patterns. And we test them on 5 different datasets that we collect ourselves. Mobile word gesture keyboard, mid-air poke within AR, mid-air poke within VR, mid-air pinch within VR, and all surface word gesture keyboard. All of them are quite large and substantial data collections. So this diverse set of data allowed us to validate the generalizability of our approaches across different environments and different interaction methods. So our results here shows that our gesture-to-text decoder achieves a top 4 accuracy of 90.4%. It significantly outperformed the SHARP2 template matching decoder and also surpassing conventional neural decoders. Additionally, our gesture-to-text, even though it's a pre-trained model, but after quantization, it can run efficiently in real time on Oculus with a latency of only 97 milliseconds and with a model size of just 4 megabytes, making it very highly suitable for practical deployment in XR systems. So why our system works? So the reason our system works so well is because it can handle noisy and unclear inputs using this coarse discretization technique. And what this really means is that we take the complex continuous gesture data, which can be really messy, and we break it down to simpler, easy to handle pixels. And by doing this, the model can more effectively learn and recognize patterns in the gestures. And this makes the system more accurate and reliable across different type of word gesture keyboards, no matter how users are interacting. So here is a simple example of how our method works. So people can see figure A is a collection trajectories for quickly, right? If we visualize it using the heat map, so figure B is the heat map visualization model output from the conventional neural decoders. And you can see that it is actually quite discretized. And figure C is the heat map visualization, one-hot encoding of the coarsely discrete trajectory for quickly. And figure D is heat map visualization model output from the pre-trained neural decoder. And as you can see that figure B and figure D are pretty similar. So which means that using a coarsely discretized and with one hot encoding, the input and the output space is already pretty aligned. So we just need to train a model to align the input and output space. Whereas if it's not coarsely encoded, coarsely discretized and one hot encoded, the input-output space are totally different, like embedding spaces. So what we did is that we align the input and output embedding space, and we train a model to learn the connection between these 2 closely related embedding space. So in conclusion, our work contributes novel generalizable decoder for word gesture keyboards in XR environments that combines high accuracy with ease of deployment. And gesture-to-text really significant outperforms existing methods in terms of accuracy and efficiency, making it ideal for real-time applications. And for future work, we plan to expand the dataset further, exploring transformer-based models and adapt the decoder to non-QWERTY layouts. Thank you. And here's my contact. I'm happy to take any questions.
Okay, any questions from the audience? So let me start with the first question. So, so if I understood it correctly, so your method can be applied to the various methods of the input modality. Is it correct?
Different modality in terms of. Yes, as long as it is on QWERTY keyboards and as long as your fingertips or whichever the contacting points can be tracked. Yes, it can be across with different interaction modalities. Yeah.
Any questions? No, do we have a question?
Hey, Sean, great talk.
Thank you.
So the discrete optimization, the discrete sort of discretization that you did was essentially a way to filter out the noise in the input, right?
Exactly, yeah.
And there are like existing filters that sort of people use to do that, like the Euro filter or something like that.
Yeah.
And I'm wondering if that is a part of your sort of pipeline already, and then on top of that, you are discretizing even more, or where does that come into the picture?
So, in terms of pipeline, do you mean in the data collection pipeline, or in terms of
are you using additional filters, or are you directly
So-
doing a discretization, and the things that you compared with, like, did they use some sort of filtering on top of the noisy input or not?
So in our data collection, so none of this prior knowledge is embedded in the data collection process. The data collection process is purely just using, say, either OptiTrack or using the HoloLens or Oculus like inbuilt hand tracking systems to collect the 2D trajectory data. So when we're doing the data collection, there is no prior knowledge built into the data collection process, and in terms of the filtering process, we don't have any filtering process. It was just all coarse discretization process when we are pre-processing the training data. So basically, how the pipeline works is that. The model, so we have a training dataset that combines a synthetic dataset and how we swipe dataset, and we use this coarse discretization pre-processing technique to convert those 2D trajectories into one-hot encoding dataset, and then that dataset is used to pre-train a LSTM-based model. So that model becomes a pre-trained decoder. And whenever that pre-trained decoder is implemented in the real-time system, and we will pre-process the inputs using the coarse discretization processing technique again, to make it be able to be fed into the model. So that's how the training pipeline and inference pipeline works.
Got it. Yeah. Thanks a lot. Thank you.
Thanks.
Okay, so we have one more question.
I'm curious. It looks like the method is pretty much device agnostic. I wonder, in the collection of the trajectories, do you need to do some sort of calibration based on the cameras, or?
No, we didn't. So as you can see, that mobile phone or just keyboard are collected using mobile phones. Mid-ear POC is collected using HoloLens 2. Mid-ear POC VR is collected using Quest 2. Mid-ear pinch is collected using Quest 2. And on surface WGK is collected using PC. We don't really do any collaborations in terms of how the fingertip is tracked. But of course, certain accuracy sort of needs to be guaranteed, so that at least like when you're doing the finger movement, it sort of needs to be in the keyboard, right? But then I think it's just that the HoloLens 2 or Quest 2 are just their inbuilt hand tracking system is already sort of, despite there's some certain latency and certain tracking inaccuracy in terms of displacement, but the noise introduced there is not as big compared to how our system can robustly decode the trajectories into the text. So I think there's a threshold. If the tracking inaccuracy is beyond that threshold, then probably our system will fail. But it's just the HoloLens 2 and the Quest 2, their tracking accuracy is still within the threshold, so our system still works pretty good on this systems. But we didn't do any pre-calibrations.
Got you. Thank you.
All right, so time's up. So let's thank our speaker. And let's move on to the second paper with the same author. So the paper is, the title is Towards Open World Gesture Recognition, and the authors are Junxiao Shen, Matthias Lange, Xuhai Su, Ren Tan, Enmin Zhou, Naveen Suda, Maciej Lazarewicz, Paola Kristensson, Amy Karlson, and Ivan Strasnick. And Junxiao Shen will be presenting.
Hi everyone, it's me again, and you'll also see me in the session later on as well, in the same session. So again, this work is a collaborative project between Meta and University of Bristol and the University of Cambridge. As Benko pointed out, that rest-one gesture recognition is very important, which is also shown by the Orion project, right? So, but the motivation here. Well, let's start with the motivation behind this work. So most existing hand gesture recognition systems really operates in closed world settings, where the assumption is that the training data and testing data comes from the same distribution. However, in real world settings, the assumption really breaks down. And if we want to make the rest-one gesture recognition really comes into play in real world, we have to throw this assumption away, right? We have to assume that the training data and testing that comes from different distributions. So we need to, instead of using static machine learning, which is usually you learn the data once, you deploy the model once, we really need to use adaptive machine learning, which is that you continuously learn the data and you continuously deploy the models. However, for adaptive machine learning, it introduces a very big challenge, which is we call it catastrophe forgetting. So what is catastrophe forgetting? Which is that while the model learns the new data, it forgets the old data pretty easily. So what you really want the model to do is that it learns the new data quickly, but at the same time, it does not forget the old data. So in this paper, we primarily focus on two real-world cases. One is called new context. The other one is called new user. So for new context, which means that while we are having a wristband, like a wristband, and for example, today we do gestures when we are walking, tomorrow running, next time on a bus, sometimes later on the plane. Under different environments, our data will change. And new data pattern will emerge. So how can we make a model to learn this new data patterns? And second real world case is for new users. Imagine, right, the wristband is probably not just for you. It can be used for your parents. It can be like shared across the family, right? But then while the new users comes in, you want the wristband to learn on their data, but also not forget the data of yourself, right? So overall, the challenge is not only includes the avoiding catastrophic forgetting, but also because it's a dynamic learning process. So there's also two key questions that we care, which is when to update the model and then also how to update the model. So traditional machine learning evaluation will not apply here because traditional machine learning models only will be evaluated in an offline fashion. But what we really want is online evaluation fashion. So our problem formulation is that we define the open world gesture recognition within a task incremental setting, where new tasks such as new contexts or new users arrive sequentially. And each task is processed in batches. And the system must handle data that is non-IID or not independent and identically distributed. Additionally, each task has its own output layer using a multi-header configuration to minimize confusion. So in order to evaluate our approach, our open word gesture recognition approach, we collected a large-scale dataset to train and evaluate our models. This includes 4 dynamic gestures: single pinch, double pinch, middle finger pinch, and face clench. Our model comes from 50 participants aged 18 to 61, performing this gesture in diverse real-world contexts, such as standing, walking, riding in a car, sitting in a car, lying on the bed, lying on a sofa, with hand up, with hand down, etc. So we also collected negative samples, such as non-gesture activities like jogging or driving, to simulate realistic environments. So we evaluated several control learning methods, first of all, to prevent casual forgetting and just to have a kind of observation. They include a baseline, which is fine-tuning. You just simply fine-tune the model on new data. And secondly, learning without forgetting. Thirdly, synaptic intelligence. Fourth is PACnet replay, and memory-aware synapses. And all of the different methods are the state-of-art control learning methods. And we did a sort of experiment on the previous data we collected. We found out that first of all, naive fine-tuning really causes forgetting of past tasks, and control learning methods they vary in effectiveness based on scenarios. So sometimes this control learning method is better, sometimes that control learning method is better, and but then, like, what if in the future some developers or designers, they want to develop their own open word gesture recognition algorithms, and they want to have some design guidelines, right? But then, as you can see here, different scenarios such as new users or new contexts, different scenarios will be compatible for different control learning methods. But then, how can we give them a good design guideline? So if they are doing it themselves, it is really resource intensive because it requires substantial time for experiments. And it also emphasizing the need for online evaluation. So what we did is that we employ a design engineering approach. And a design engineering approach is usually used to assess a process that is challenging to evaluate via user studies. And we can use a design engineering approach to evaluate this open word gesture recognition in an offline fashion and to study the effects of different parameters. So we use design engineering to decouple the open word gesture recognition into 5 stages. First, device deployment. Second, data logging. Third, data creation, retraining trigger, and updating policy. And the critical design consideration here are the 4th and 5th step, which is when and how to update the model to balance learning new data without forgetting past tasks. So let's take a closer look at the surrogate task model we use to evaluate control learning methods in open word gesture recognition. The model evaluates 3 key aspects. One is granularity of tasks. Second is order of tasks. And third is number of tasks. So granularity of tasks is like, if you want to define the task into coarse or fine tasks, such as like standing is like a coarse task. But then also you can define it to be very fine tasks. It's like standing with hand up, standing with hand down. And order of tasks, it can be easier to hard tasks or it can be just random tasks. So there are all the parameters of the open word gesture recognition. By changing the parameters of the granularity of tasks, order of tasks, and number of tasks, we can then really study how the different parameters of the open word gesture recognition can bring effects to the real world applications. So our evaluation metrics include the accuracy to measure the ability to transfer knowledge from old tasks to new tasks, and also forgetting, which is the model's loss of performance on previous learned tasks. So I'm going to skip the actual figures in our paper, because the actual figures in our paper is pretty. There's a lot of figures, and also there's a lot of data points on there. So I'm just going to jump straight to discussion and key insights. So our method is mainly to balance is to strike a balance between stability and plasticity. Stability is to retain previously learned knowledge without forgetting, and plasticity is the ability to learn new tasks without overfitting to old data. And we provide design guidelines. The design guidelines for when to update is that coarse contexts often yield better results, and task boundaries are defined by descriptors. And in terms of how to update is that for new context scenario, replay method is better for best accuracy, and PackNet is for balancing accuracy and forgetting. And for new user scenario, PackNet and learning without forgetting perform well, maintaining low forgetting and high accuracy. And all of these are performed through envelope analysis. And envelope analysis is really important and is a very good practical alternative to large-scale user studies, offering flexibility in parameter evaluations, and also it facilitates systematic exploration of open world gesture recognition without resource-intensive deployments. Thank you.
Okay, so we have some minutes for questions. So do we have questions from the audience?
Another great talk.
Thank you.
Yeah, Michael Prue from Reality Labs. Another form of useful plasticity could be being able to handle different sensor types or sensor arrangements or numbers of sensors. I'm curious whether you think the approach you're using could address that sort of problem as well.
What kind of sensor pipes do you mean?
Well, like if you're using, say, IMU versus switching to, say, camera-based sensors for such gestures that could be recognized by a system, or any other approach that might be used.
Yeah, I think, and despite our paper only investigating into IMU signals, but the control learning framework actually applies to different modalities, because to the model itself, it's only a matter of how the input modality changes. But then as long as you change some of the input layers, their intermediate embedding are or just metrics. So our framework actually applies to different modalities. And also this is one of our future work that we really want to apply this framework to, say, EMGs and videos and etc. Yeah, thanks.
Okay. We have other questions? Okay, so I have a question. So could you share your insight on the open world problem about like how you can extend what you have experienced to the other problems other than gesture recognition?
You mean for open world problems
For
apart from gesture recognition?
Right.
Right. So, so I think open world is a problem. Is really a very hard problem because most of our studies are actually conducted in the very closed lab settings, and probably while we are conducting user studies under lab settings, the user's reflections on or user behavior patterns on our systems might be very different towards how they would react in the open world. Because in the open world, there's also a lot of other factors to be considered in. So I think this is just a very big gap between open world and closed world. So I'm also now exploring new methods to how to close the gap or at least how to minimize the gap. Say, can we simulate a realistic agent and to simulate a realistic agent to operate in a kind of simulated open world So to make it an open world, but at the same time, we can control a lot of the parameters. So we are actually like explore this kind of ways to discover new methods for open world settings. But yeah, it's a very hard question, I think.
Okay, great answer. If we don't have further question, then let's thank our speaker. So the third paper is, the authors are not here, and we're gonna play a video, I think. So the title of the paper is Tasks Reflected in the Eyes, Egocentric Gaze-Aware Visual Task Type Recognition in Virtual Reality. The authors are Jimin Wang and Feng Lu.
Visual tasks. One of the earliest studies pro researcher from. Hello everyone, I'm Jimin Wang, a postdoctoral researcher from Beihang University. The paper I will be presenting today is titled Tasks Reflected in the Eyes, Egocentric Gaze-Aware Visual Task Type Recognition in Virtual Reality. My talk will be in 7 parts. Firstly, I will introduce the background. Eye tracking technology has proven to be effective in recognizing users' visual tasks. One of the earliest studies in this area was conducted by Yabas in 1967. He demonstrated that eye movements vary significantly based on the particular task a person is performing. Recognizing visual tasks in XR systems is crucial for creating adaptive contact and low-friction user interfaces. And shown in this video, if the system detects that a user is viewing a painting, it could enhance immersive experiences by playing coordinating music. Similarly, if a user is reading a text, the system could display navigation buttons for turning pages. Several researchers have investigated task recognition using eye tracking data. Boolean et al. Recognized tasks like copying, reading, and web browsing in an office setting using eye tracking metrics such as fixations and cigars. Mapika et al. Recognized tasks like free exploration, memory, and visual research in indoor corridor using hand orientations and gaze directions. While these studies demonstrate that adaptability of eye tracking in various environments, they also reveal certain limitations. Many studies primarily focus on sense-specific tasks, such as those designed for office environments or specific VR experiences. This limits their utility across diverse scenarios. Additionally, most studies assume participants perform only one task at a time, which doesn't reflect real-world situations where users often switch between tasks. Overcoming these challenges emphasizes the need for more practical solutions. In our work, we propose for sense-agnostic visual task types for VR systems, enabling task type recognition in a broader range of scenarios. We also create a new dataset with precise temporal boundaries for multiple task types, supporting free task switching. Additionally, we introduce tree-clip, a learning-based approach that outperforms existing methods and show its practical use through 3 examples. We visualized the eye movement trajectories as users perform different visual tasks. We noticed distinct patterns across tasks like focusing on a TV, free exploration, and counting items. However, we also found similar tasks, such as tracking a bicycle rider or tracking a walker, showed similar patterns. These observations inspired us to clarify these tasks using specific rules. We define 4 task types based on object states and eye movement patterns, that is, fixating on stationary object, tracking a moving object, observing sequential objects, and free exploration. Fixating involves long fixations on a still object, while tracking involves smoothing pursuit of a moving object. Observing sequential objects involves sequential cigars and short fixations, while free exploration involves irregular cigars and short fixations. To gather data for these task types, we select 15 360-degree VR videos of real-world scenes, such as basketball match, street scenes, and stations. In addition to these videos, we use 10 text images for reading tasks. However, since visual tasks are highly subjective and user-dependent, it's challenging to accurately determine tasks and task switching moments during post-hoc annotation. To solve this, we propose a 2-stage annotation process. First, in pre-annotation, we annotate all possible time intervals and task instructions. Then, during user annotation, users are presented with random tasks and are responsible for determining the start and end times of each task. This method ensures accurate taper boundaries for task switching. During data collection, we recorded several types of data, including eye-in head data, gaze-in world data, head orientation data, and task type labels. We recorded 20 participants. Each participant watched 12 randomly selected videos from 50 videos while performing randomly assigned tasks. In total, we obtained 240 records, with each video being viewed by 60 participants. To recognize task types, we apply a contrastive feature extraction method. This involves temporal data augmentation and contrastive learning to extract gaze features. For task type recognition, we design a network using CNN, Big Rule, and MLP. Furthermore, we implement a post-optimization step to smooth the recognition results. While other methods perform best with a 6-second window, our method excels with a 2-second window, allowing predictions 4 seconds earlier. With this window, we improve accuracy by 4.3% and 3.5% respectively over the second-best method. Additionally, the 2-second window reduces time delays by 0.5 seconds. Although our method shows high accuracy, there is some confusion between observing sequential objects and tracking a moving object, especially when object speed exceeds 30 degrees per second, making smooth pursuit to become cigarettes. Our ablation study shows the contribution of each model component, with post-optimization offering the most improvement. This example shows the eye movement trajectories of a user while performing 4 task types in the VR video of the underwater world.
The proposed triclip recognizes 4 visual task types, including fixating, observing, tracking, and free exploration. It supports seamless switching among these multiple task types. This section presents the task type recognition results obtained through the triclip method. In example 1, the system combines task type recognition and object detection to infer that the user is fixating on a television. This triggers an assistance to recommend discounted television products. In example 2, the system combines recognized task type and gaze target detection to infer the user is reading text. This triggers an assistance that highlights the reading line to enhance user focus. In example 3, by inferring that the user is tracking a person, the system triggers an assistance that displays the bounding box and historical movement trajectory of the tracked object.
In future work, we will introduce gaze target detection to better differentiate between overlapping eye movements. We will also explore scenarios with user movement to better reflect real-world conditions. We will investigate the recognition of additional task types involving irregular cigarettes. Thank you.
So the authors are waiting for question and answer, right? Okay. So can we see the authors? Right. So if you have questions, then we can interact with them. So raise your hand if you have a question. Hi, can you hear us? Looks like you cannot hear from him. Hi, can you try to talk over there? Oh, looks like yeah, we are not hearing from him. So Jimmy, can you hear us? Looks like he can hear us. Yeah, he's right. Yeah. Anyways, if you have any question, then you can at least talk to him. Oh, we have a Discord channel, so if you have a question, then you can upload your question to Discord, right? So that you can get the answer from the authors. Unfortunately, we need to move on to the next paper. So, yeah, at least we saw the author. Right. Right. So. Okay, let's move on to the next paper. The final paper of this session is predicting locomotion intention and using eye movements and EEG with LSTM and Transformers. The authors are Gianni Bremer and Marcus Leppi. And Gianni will be presenting. Okay.
Do you have audio in your presentation? Okay. Need a clicker. You have HDMI out on the side or on the back? Okay, great.
Okay, I'm Johnny, and my topic is predicting locomotion intention using eye movements and EEG with LSTM and Transformers. And I'd like to start by presenting the idea of the paper. So we want to predict where someone is moving, and if the person is going to the right, to the left, if it's slow or fast. And we use 3 different types of data sources in order to do this. So one is the history of locomotion data. The second one would be eye tracking data. And the third one we wanted to evaluate is EEG recordings. We fed all of these into deep learning neural network models and then predicted the future paths. So the paths were like two-dimensional streams of the locomotion. So we had like a sequence of X values and a sequence of Y values as our output. Okay, why would you even want to do that? So one idea that you could have is to optimize processes inside of virtual reality. For example, redirected walking, which is I don't know if you're familiar, it's a paradigm in which you display a different visual input to the user, so the user changes his or her path in order to not collide with a wall. And this works better the sooner you can say in which direction you want to redirect him. So predicting where someone will go in the near future could be really helpful to optimize systems like these. But that's not our main application context. The main application context we had in mind is an electronic wheelchair that can be steered without your hands, without even using a joystick or something like that, for patients with motor impairments, for example. So that wheelchair would be steered through your eyes and possibly also your brain data. And we also wanted to display feedback to the user about the prediction of the model through an augmented reality device. So this could be to enhance safety and to make the user feel more comfortable and make the user able to adapt to the predictions of the model. Okay, first we started with 2 data collection experiments. We collected the locomotion ground truth using a joystick. We had a virtual reality device with an integrated eye tracker measuring the eye data. And we had a 32-channel wet electrode EEG. And these are the 2 data collection experiments we used. The first one is this forest task. So the blue ray is the eye tracking. And the task here, that the instructions are really minimal here. So the users had to gather these red fruits or red balls or whatever you want to call them. And they were free to decide which fruit to get, which ball to gather. So there was not much of an instruction given here. They could move however they want. And this is in contrast to the second experiment we conducted, in which there is a pre-given task, a pre-given path. This is this black line on the ground. The users were instructed to follow it, and it is made from Microsoft GeoLive data set. So this is real GPS data of people that were walking, not the people we tested in our lab, but it's real data. And there's a double task here. So the users not only have to follow that black path, but they also have to look at these gray pillars to the side of the path and count the stripes on these pillars. There are many of these pillars with 2 stripes, and some of them have 3 stripes, and the users had to count how many there were 3 stripes. The only reason for this search task was that we wanted to have 2 distinct types of eye movements. So there are eye movements that are indicative of locomotor intention, which are directed at the black path, and there are another set of eye movements that are explicitly not indicative of locomotor intention because they are directed at these pillars. Yeah, we fed the history of positions and the eye tracking into a deep learning model. This could be a transformer like here or an LSTM model. And we also fed the EEG data into that. So we applied high-pass and low-pass filtering and gave it into a convolutional layer to put it into the transformer or LSTM model. And we also conducted time frequency analysis and then put that into the model. This is all we could do. It could be processed in real time, because if you want to have that wheelchair running, all of that has to work in real time. So you can't do something like ICA or something like that. Okay, and these are the results. So on the x-axis, you see the time into the future, which means the samples that we were predicting. So for example, if you only want to predict the next few frames, it's much, much easier compared to predicting the next 4 seconds of information where someone is going. Obviously, the noise and the difficulty increases there. And on the y-axis, you have the relative error, which is just the error in meters divided by the distance traveled. So for example, if you have an error of 1 meter between the ground truth and the prediction, if you have traveled a distance of 1 meter, this is really bad. This is basically guessing. However, if you traveled 100 meters and you have an error of 1 meter, this is really good. So that's why we do that relative error. First of all, deep learning methods outperformed some simple methods like autoregression. And secondly, the transformer outperformed the LSTM architecture a little bit. This is statistically significant. However, as you can see, it's a fairly small difference. Next, we evaluated different features. This is the relative error after 4 seconds. And let me start from the left to the right. So in purple and pink, we have the models with position and eye data and the model with position, eye, and EEG data. Those were the best performing models. Then in red, we have a model with position and EEG data, and in brown, the model only using positional data. And then after that, only using eyes and only using EEG data. So what we can gather from that is that the best performing feature without the others was the history of position data. That's probably pretty trivial, and then we can get that eye data was better than EEG data. And the most important thing here is probably that whenever you had a model that already had access to eye data, adding EEG data on top of that model wouldn't give us any improvement in accuracy. And this was kind of rare to us. So we investigated what was happening, because adding the EEG data to the positional model and having it on its own had clearly some benefit. And when you look at the absolute rates of the EEG channels of the first convolutional layer, you have a projection of this on the right. We saw that by far the most important electrodes were the electrodes that were placed right above the eyes. So obviously a deep learning model is a black box, but what I think is happening here is that this is not an EEG measurement at all. It kind of builds its own little EOG. So it takes the electric potentials of the eyes moving and then uses that. And adding that to infrared eye tracking data obviously has no benefit. That is why, yeah, the sources of data were so similar. In addition to that, we wanted to evaluate the generalization performance. So on the left, you just see in this messy figure how the performance from the forest and the Coarse experiments, and this is pretty much the same, so the lines are on top of each other. This is also the same if you remove eye data. And much more interesting is what you can see on the right here. So in blue, we have a model that was trained on the forest experiment and evaluated on the coarse task. And we can see that it still performs pretty well. It generalizes pretty well. The error here is similar to the overall error. But that changes when you have the exact opposite, a model that was trained on the coarse task and evaluated on the forest task. This is the green line, performs much worse. And our interpretation of this is that the forest task had a very wide array of different movement types. You could move whatever you want, and there was a wide distribution of movement types, and that was generalized pretty well to the coarse task. The coarse task, on the other hand, had these predefined black paths, and some types of movements, some movement scenarios were just not there. So the generalization to the forest task, on the other hand, was really poor. Yeah. I also wanted to show you this. This is a pseudo online run. So I hope you can see this little pink line. These are the predictions. And I wanted to show this because this is what you, for example, could display on an augmented reality headset for the user to see the feedback, to see how the prediction is working. And this is the application that we wanna work on. So you have a wheelchair and you don't steer it with a joystick or anything like that. Instead of that, you just use your eye or your eye and brain data, and the model then gives you your future position and steers the wheelchair for you. This is what we're working on right now. Okay. So to conclude, we have 3 major findings. Gaze data is a really valuable tool for locomotion prediction. Transformers achieved the best performance. And successful prediction requires data sets containing a wide range of movement scenarios. Thank you for your attention.
Okay, so do we have questions?
Hello, thank you very much for your presentation. Very impressive work. I had a question regarding the EEG. So as you showed, well, it's more EOGs than EEG. What kind of plan do you have to have an EEG that is actually useful and not just high movement, with keeping with, let's say, real-time, or as close as possible to real-time? What kind of work can be done, pre-processing, post-processing, something in the transformer itself? What can we expect?
Yeah, so what makes it really hard is that the best methods to pre-process EEG, and what many people are using in this offline analysis, like independent component analysis and then filtering it all, I couldn't find a way to make them work in real time in a scenario where the deep learning model has to run and everything like that. So we won't do that. So what we did, what could work in real time, was just simple filtering and some Fourier analysis to get like time frequency analysis. So for where we are at now in this project, both of these didn't really give an advantage that was complementary to eye tracking data. There was some information contained in that, but it's not complementary to eye tracking data. So I guess we have to figure out better methods to maybe preprocessors. Maybe the answer is just having a larger collection of data, or having the EEG part of the model pre-trained and giving the model a better idea about what to make of this EEG data. Yeah, right now we're mostly working with eye tracking data because it's also much easier to collect. Like, you don't have to apply a red electrode EEG. That's convenient. Yeah.
Thank you very much.
Oh, actually, you raised the hand first, right? Next is you.
Hi, thank you for your nice talk. So I am wondering, so you show some demo for real-time prediction. So which model you actually deploy for the real-time prediction?
Sorry, could you repeat that?
So you show some video demo, so where you show like there is a real-time prediction of some sort of location, I think.
This one or the one before?
Yeah, this one, yeah.
This one, okay.
Yeah. So you deploy the model in the VR headset, or like for the prediction, real-time prediction?
Yeah, this is a pseudo online run, meaning this is data from one of the subjects, and we applied the model at every time step and got this pink line, this prediction.
Oh, it's a real-time prediction, or?
Sorry, could you repeat that?
It's a real-time prediction, so like you have a streaming eye tracking data or whatever the VR data, and then you do the prediction?
It's a continuous prediction using a stream of eye tracking data and the history of locomotion data.
Yeah, so which model you are using here? Transformer or LSTM?
Oh, this is the transformer model. We ultimately decided that while both of them perform very similar, the transformer was a tiny bit better, so everything else was evaluated with the transformer. Good question. Also, this features and this stuff, this is all based on transformers.
Yeah, so my question is like that, since you are deploying for instance, you are deploying the VR headset for a LST, so deep learning model, it's like computationally heavy, yeah? For instance, like, do you calculate the latency of the prediction, like how much take time for the prediction?
How much time it takes to make the prediction?
Yeah, for instance, per frame or whatever.
Yeah,
like
we calculate that it's way under a frame. It's like, I think it's somewhere in the paper, the actual prediction, because the model is pretty small. It's a transformer, but like the number of attentional heads and all of this is pretty small. And in inference, it doesn't take a significant amount of time to calculate that. So it's, the VR headset is running at 90 Hertz and it's way below 1 frame.
Okay, thank you.
Okay, so we have a final, last question.
Okay, sorry. Can you hear me? Okay, thank you very much. Really great talk. And I have maybe a strange question, because you have the eye tracking data and EEG, so the combinations of these two data sets. And is there any chance to kind of, you train the model to clean up the EEG data, which related to the eye movement, that you can, I'm not sure, we can only have the useful EEG data for any other task? Because I think, yeah, this is a really common problem that we're using EEG data, because there's a lot of eye-related noises inside the EEG feature. So how do you think about that?
Yeah, that's a really interesting thought. I like that idea, to clean the eye movement artifacts in the EEG using the eye tracking data from the infrared eye tracking. There is like a few milliseconds of delay between those, because at least the Vive, and I think the HoloLens as well, gives us the eye tracking data with a delay. But in theory, you could do that. We didn't attempt that because my thinking was, if there is something in the EEG, even if it's not related to the brain in and of itself, that is beneficial for prediction, why throw it out? But maybe it's actually better to apply this. And maybe this is much easier than doing like ICA filtering. It's probably more computationally easier. So yeah, thank you, good idea.
Right, so it's time for break. So that concludes the session, and let's thank our speaker again. So the speakers will be here for a while. If you have further questions, then please come up here to communicate with the authors.